Okay, so this is the section on tangential velocity and tangential acceleration, which these are going to deal with that issue of an object having different speeds at different positions on a rotating uh, disk or whatever object, whatever it might be. So if we have some angle, so we know that if we have some angle delta theta here, delta theta, if this is r, then this length here we would call delta s, the arc length. So previously we defined angular velocity, and it was dependent on the delta theta per time. So any point along, or any point that traces out the same delta theta angle is going to have the same angular velocity. So now we're looking at what is the speed happening according to the distance covered by the arc length. So let's just recall the relationship real quick. Delta theta is equal to delta s per radius, or divided by the radius. So if I consider delta theta per time, which is what we had defined angular velocity as, but now we want to consider it in terms of the delta s distance, not like an angle displacement, but the actual displacement of some object riding along this arc length. So we would have 1 over r times delta s over delta t. It's just the same thing as this with an extra, just divided both sides by delta t, kind of to see what's going to happen here. So this side over here is called, that is what we defined as angular velocity. And over here, this is an actual position, or well, displacement of two positions. This is not an angle measure. This measure, delta s, actually has like units, like meters attached to it. So delta s over delta t describes a velocity. Well, I'll say it this way, describes the movement of an object, well, an object. So the object being the thing that's riding along the edge of the disk or somewhere on the disk per unit time. Or I'll just say per time. That's what this little fraction represents. That's a displacement per time, aka velocity. So we can say that we have this relationship. Angular velocity is equal to the velocity in terms of the arc length, described by the arc length here, divided by the radius. So just to keep things straight, we'll think of v as being like the linear speed, and this as being the, or linear velocity, I should say, and this as being the angular velocity. So angular velocity is equal to linear velocity divided by the radius. So typically this relationship is written like this. V is equal to omega r, angular velocity times, it's the same relationship, just this is the more typical way of writing it. And then we like to stick a t there for tangential, and the reason for that is the linear velocity is always tangent to the circle, to the so-called circular path. So if I draw some object and it's tracing out some arc length here, so let's just say it goes from there to there, so its displacement would be the delta s, and it's doing that over some time. So its velocity at each point is going to be tangent to the circle. It always points tangent to the point on the circle. So if it, like right here, it would be like this, always pointing, so its direction is ever changing as it moves. Its direction is always going to be changing. And what does that mean for us here? Well, that's what the t means, tangential. So you can call it tangential velocity, linear velocity. It just kind of depends on the context of how you're talking about it, but they're pretty much the same thing. So the tangential velocity is equal to the angular velocity times radius. The radius being how far the object is from the point at which the disk is spinning. So just to have a picture to really hammer this point home, if we have some circle centered here, and it's spinning, let's just say it's spinning counterclockwise to keep things positive, then as it spins, this point P and maybe this point Q all the way over here, P and Q will have the same angular velocity, omega, but P will have a lower tangential velocity. Than Q. Maybe I should say tangential velocity, and we'll name V sub t, then Q. So the further something is from the center, the higher its tangential velocity. Okay, so and that checks out with this relationship, right? As r increases, tangential velocity increases, while angular velocity remains constant for any point on this circle, or on the disk, whatever it might be. Okay, so we can define angular velocity, tangential acceleration is what I meant to say, very similarly by saying, well, let's look at this relationship. Vt is equal to, delta. Let's look at a change in tangential velocity should be equal to a change in angular velocity. Okay. So when I say change in tangential velocity, I mean like a final minus initial should be equal to, and now this is just for the moment how we're defining what a change in tangential velocity would be. This is not saying, oh, well, the change would be 0 because it's the same everywhere. It's a different context here. We're changing gears, just thinking about building up the definition that's going to relate tangential acceleration to angular acceleration. So what I do from here is I say, well, I can divide both sides by delta t. The whole point of doing that is saying, well, this term, some changing velocity divided by time, that is the definition of acceleration. In fact, we'll call it the tangential acceleration, and that's going to be equal to r alpha. Because from last video or last section, this was equal to, by definition to alpha. So we have these really nice relationships coming out relating the tangential thing to its analogous angular definition, right? So basically they're exactly the same, except you're just tacking an r on to the angular one to make them equal. The same thing's happening here. All right. Okay, I want to look at this quick quiz here. It says quick quiz. Part 7.4 says Andrea and Chuck are riding on a merry-go-round. Andrea rides on a horse at the outer rim of the circular platform, twice as far from the center, so her radius is larger, twice as large, than Chuck, who rides on an inner horse. When the merry-go-round is rotated at a constant angular speed, Andrea's angular speed is, and then we have some options here, A, B, or C, or D. So twice, the same, half. Well, that's exactly what I wrote on this picture here, right? They have the same angular velocity. They have the same angular velocity. Now 7.5 says when the merry-go-round is rotating at a constant angular speed, Andrea's tangential speed, what would that be? Well, her tangential speed is dependent on the radius. Since she's twice as far away, her speed would be twice whatever Chuck's was. Her tangential speed will be twice. Okay, so here's a problem involving a compact disk that rotates from rest up to an angular velocity of negative 31.4 radians per second in a time of 0.892 seconds. They want the angular acceleration, assuming it's constant, uniform, not a changing acceleration. Okay, so I know that I have an initial, part A, angular acceleration is equal to, change in, let me write that a little bit better. Angular acceleration is equal to change in omega, angular velocity divided by change in time. It starts from rest, so initial velocity, angular velocity is 0, and its final angular velocity is that negative 31.4. So there's those two values. And time initial is just time 0. So my final time minus my initial time looks like that. And that's going to be negative, what is that, 35.2 radians per second squared. Okay. Straight from the definition of angular acceleration. Now, part B says through what angle does the disk turn while it's coming up to this speed? Well, so I'm looking for delta theta. And I'm thinking that delta theta doesn't, like, I can't fall back on this kind of definition, right? Delta theta is just like the most bare bones definition, angular displacement. So probably need kinematics, which is fine because I have pretty much everything else I could want. I have acceleration, I have time, and I have initial and final velocity. So I'll say delta theta is equal to, just looking at those kinematic equations, omega initial times t plus 1/2 alpha t squared. That's going to 0 plus 1/2 times negative 35.2 times 0.892 squared. Okay, and that's giving me negative 14 radians, 14.0 radians. Okay, so first term being 0 because initial angular velocity was 0. And it doesn't make sense that it's a negative displacement. Like that means this thing is rotating clockwise. Does that check out with what's happening in the problem? Well, they gave us a negative velocity, so it is rotating clockwise. So that makes sense. In fact, it's speeding up in the clockwise direction because the velocity went from rest, speeding up in the clockwise direction via this acceleration, and after 0.892 seconds ends up at this angular velocity in the clockwise direction, covering this many radians, which is roughly, 2.5 revolutions or so. It didn't ask for revolutions, so okay. if the radius of the disk is 4.45 centimeters, find the tangential velocity of a microbe riding on the rim of the disk at that same time. So part C, tangential velocity is equal to omega r. So at the time given, we have omega is that negative 31.4 radians. Or not radians, radians per second. Sorry, that's radians per second. And then r is the radius, which they say, so it's not necessarily going to be the radius of the disk. It's the radius of the object that's riding on the disk. It just so happens that the microbe is on the rim of the disk. So we will just plug in the radius of the disk. Okay. What I mean by that is it's the radius is 4.45 centimeters, and the object, or the microbe, is right on the edge. So that's the radius that it's at. If it was closer, we would need to use a different value for r. But since it's right on the rim, then we just use that same number. So 0.045 meters, converting to meters. I didn't write the units here, so I probably shouldn't have written them there, but just wanted to emphasize that centimeters turned into meters. And then that's giving us, hang on, I wrote this wrong. Hang on. I wrote the number down wrong. 0.0445. There we go. Okay. And that is negative 1.40 meters per second. Not radians per second, because this is a tangential velocity. It's measured in meters per second. So maybe something to point out here is that you might notice these signs should agree. The sign of tangential velocity is going to be dictated by the sign of angular velocity, because r is always going to be positive. R is a radius, so it's always going to be positive. So if angular velocity is negative clockwise, then tangential velocity will end up being negative. Okay, so part D asks, what is the magnitude of the tangential acceleration of the microbe at the given time of 0.892 seconds? Well, tangential acceleration is equal to alpha times r, or r times alpha, whichever, which is equal to, what did we get for alpha? It was negative 35.2, yeah, radians per second squared, and then times 0.0445 meters, that's the radius there, and that's going to give us a negative 1.57 meters per second squared. So again, noting omega is determined by radians per second, alpha radians per second squared, and tangential velocity meters per second, and acceleration, tangential acceleration meters per second squared. Okay, so that problem pretty much just straight from definitions, a little bit of kinematics. Okay, so now we need to talk about centripetal acceleration, but first just consider that you have some object moving around, so now we're thinking less about the entire disk spinning and thinking more about like changing the reference a little bit to think about the object on the disk that's moving, or you could think about it as a car under its own power moving around in a circle. So if the object's tangential velocity is changing, so, or wait, is that what I mean to say? In magnitude is what I mean. Changing in magnitude, then there is tangential acceleration, right? So if the object is going around, it's got some velocity vector v sub t initial, and then maybe up here it's changing in magnitude, it's much faster, v sub t. Oops, v sub t final. V sub t final is what that's supposed to say for a tangential velocity final. So the magnitude is changing, so there is a non-zero tangential acceleration. The tangential acceleration here is not zero. Okay. Then, okay, now if I have object here, so if the objects tangential velocity is not changing, then there is no tangential acceleration. So for instance, whoops, draw a little bit better here. So maybe that's v tangential initial. And then up here, same magnitude, v tangential final. Then there is no tangential acceleration, meaning it's zero. However, in any case, in either case, there is centripetal acceleration, pointing towards the center. So here, let's see. So here, I should put the center of the circle just for reference. It's going to point towards the center of the circle in any case. That way, I should also say that in this case, the acceleration vector here is pointing for this non-zero tangential acceleration. It's pointing in the same direction as the velocity. I'll draw a better picture of that in a second. Now, it does not exist down here, right? So I won't draw it here. So the point being, though, that whether or not there is tangential acceleration, in this case there is, in this case there's not, there's always going to be centripetal acceleration pointing towards the center of the circle. Now, without getting too crazy with the derivations, centripetal acceleration is going to be equal to v, in terms of the velocity v, it's v squared over r, and in terms of angular physical definitions, and it's going to be r omega squared. It just depends on the context of the problem, which one you would use here. Now, let's talk a little bit more about this case where there is both centripetal acceleration and tangential acceleration. So in that case where you have both, let me redraw that circle, but only draw their acceleration vectors on there just to make the picture a little bit easier to read. So this time I'll just say like, okay, here is some tangential acceleration, so I'll call it a sub t, so ignoring velocities, and then some other, now we want the acceleration to stay constant because otherwise things get weird, so this still represents the same picture where velocities are increasing because we have a positive acceleration, and the acceleration here is non-zero, it's some constant non-zero. And then we have the centripetal acceleration pointing towards the middle. And it's no coincidence, whoops, these should be the same in length. These two are red ones are the same in length, blue ones are the same in length. They don't have to be the same length as each other, it's just like blue doesn't have to be equal to red. Could be, doesn't have to be. Okay, so it should look like these things are perpendicular to each other, and they are, because this one is always going to be pointing tangent to the circle, and the other one's pointing straight in. So by the geometry here, these are always going to be perpendicular to each other. So I'll say, with the condition that when it exists, because sometimes it doesn't exist, tangential velocity, tangential acceleration. So when it exists, when it's not zero, like in that first circle I drew, when the object is speeding up around, or slowing down, I guess, around the circle, tangential acceleration is perpendicular to centripetal acceleration. Why am I pointing that out? Well, because we're going to have a new type of one more new type of acceleration that relates these two. In this case, when you have both types, the total acceleration is given by, well, if they're perpendicular to each other, we can find the hypotenuse, that'll be the total acceleration. Let me see what they call it, a sub t, it can't be a sub t, what do they just call it a, okay, a is equal to the square root of a t squared plus a c squared. That's coming from the a sub c, a sub t, and then the hypotenuse. So these are perpendicular, so the hypotenuse given here by just a, as I've drawn it here. Okay. Alright, so again I want to look at one of these quick quiz things because they're pretty good conceptual things. So looking right here. So using this picture, a racetrack is constructed such that two arcs of radius 80 meters at what they're calling position A and B is 40 meter radius arc are joined by two stretches of straight track. In a particular trial run, a driver travels at a constant speed of 50 meters per second for one complete lap. So we should pause there and say, is that an angular velocity or a tangential velocity? Well, since they say meters per second, we know it's a tangential velocity. So this is the case when we have no tangential acceleration because the tangential velocity is not changing in magnitude. Oh my gosh, did I even say why? So there's always centripetal acceleration because the velocity vector is always changing direction. I don't know if I said that, but yeah. So that's why centripetal acceleration always exists, because movement around a curve means that you're changing direction. So just by definition, technically, there is acceleration, and technically is enough to mean you get your own definition in physics, and it has to be pointed out. Okay, so right, what are we doing here now? Okay, so we have a constant velocity, meaning zero tangential acceleration. All right, so let's see what the questions ask. Part 1 says we want the ratio of the tangential acceleration at a, well, they're both 0. So that's the answer for that one. They're both 0. Tangential acceleration is 0 if the tangential velocity is constant. Part 2 says the ratio of the centripetal acceleration, okay, for part A to part B. So that's a little bit more interesting. The tangential, or no, sorry, the centripetal acceleration, A sub c, is equal to, well, what do we want the v squared over r, because we're dealing with tangential, that is tangential velocity. The book leaves off the t, not really sure why, but it's still just tangential velocity. So we want the ratio of A to the ratio of B, of these centripetal accelerations. That's what we want here, the ratio of the centripetal acceleration at A. And what's different about them? The radius, right? The radius. One has radius 80 at A, and the other is radius 40. V squared is going to be the same. So we have this ratio being velocity at part A squared over r at A, all over velocity at part B squared all over r sub B. This is equal to, well, they're both the same velocities, so let me just not subscript them by letters and just call each of them a v, because they're going to be the same. So r sub A over, when we give them their own subscript names, it implies that they're different. So I'll write them without subscripts so that I understand that they are the same. And now I'll, okay, squish myself into a corner over here. So now I'll say, well, v squared over RA times RB over b squared. Just division by two fractions means you multiply the top fraction by the bottom fraction, except inverted. So that's just fraction division there, and then we get the v squareds canceling. Okay, so we're getting RB over RA, and that's going to be 40 meters over 80 meters, which boils down to 1/2. So it's less. So let's see if that makes physical sense. So what we're saying here is that we just compared the centripetal acceleration here to here and said it's half. So it's twice as fast over here, half as fast over here. Does that make, well, when I say as fast, I mean the centripetal acceleration. So does that make sense? Well, if we consider the definition of centripetal acceleration, it makes sense because we're dividing by r. So dividing by a bigger radius means that you have less centripetal acceleration. Dividing by a smaller radius gives you more centripetal acceleration. Consider that this thing is moving at a constant speed, right? So it's as if it has more time to get around this curve. So if it goes over here, it's got to kind of, to maintain a constant tangential velocity, it kind of whips around small turns. And you know that if you think about driving in a car, if you're going constantly 60 miles an hour, say, around this, wouldn't you think that you would experience much less acceleration going around this? And when I say I mean the centripetal acceleration. In other words, this would feel like a much easier turn to make than this one where you kind of whip around that smaller radius. So it does make sense that larger radius gives less centripetal acceleration. Now the angular speed is greatest at a, b, or equal. Angular speed is determined by, well, angular speed is there. So we can reorder this. I think I wrote this one down already somewhere, but there it is. There's angular speed. Now this is constant, right? In this problem, tangential velocity was given as constant. Radius is changing. Again, it's like the same argument. Where is the radius the smallest? Because that will make this the biggest, because we're dividing by it. So it's going to be a similar argument that the angular speed is going to be is that right? Yes. Right, okay, so now I'm going to look at this problem. So write it down here so we can see it better. Okay, so a race car accelerates uniformly from a speed of 40 meters per second to 60 meters per second in 5 seconds while traveling counterclockwise around a circular track of radius 4 times 10 to the second meters, 400 meters. When the car reaches 50 meters per second, calculate the magnitude of the centripetal acceleration. So I just abbreviated that A sub c for centripetal acceleration. Then they're going to want some other stuff too at that same speed. So part A, looking for centripetal acceleration, well, I'm given A sub c, I'm given the speed, tangential speed that I'm looking for, so, and I'm given radius, so I'll use those. I'll just use this equation. No need to get these involved, at least not yet. Because centripetal acceleration will be determined by the speed that you are currently going, and that's really what we want. Now, if they ask for, what might they ask for? The tangential acceleration, which I believe they do in part C, that's when we'll get this these two different speeds going. Okay, so the centripetal acceleration at the, I'm just going to say equals here, at that speed of 50 meters per second is going to be 50 squared over, I'm just going to go ahead and say 400 for 4 times 10 squared meters, so that's the radius. And that's going to be 6.25 meters per second squared. Okay, so part B asks for the angular velocity, so omega, and I'm given the current tangential velocity, and I know this is the relationship, so just falling back on that relationship, and I'm getting 50 meters per second over 400. So just coming from these 0.15 meters, no, not meters per second, radians per second. Just coming from these definitions here, that's where I'm getting these. And also understanding that the centripetal acceleration is due not to a change in magnitude of tangential velocity. That's not what that's what tangential acceleration is for. and that's what we're about to calculate in part C. Centripetal accelerations happens at a particular velocity, and they specifically asked about this. Now, they also say to find the magnitude of tangential acceleration, and they say when the car reaches 50 meters per second, calculate the magnitude of tangential acceleration. So what do we use? Well, it's passing through that velocity on its way from 40 to 60. That's how we're going to calculate tangential acceleration. We're going to treat it as a difference of velocities per time. Oh, do we know time? Oh yeah, 5 seconds. Okay. So we'll say delta v tangential velocity change over delta t, which is going to be that 60 minus 40, delta t being just 5 seconds, right? So starts, well, it doesn't start from rest, but at time 0 it's at 40 meters per second, and then at time 5 seconds it's at 60, so 5 minus 0. So we're getting 20 over 5, so 4. We're keeping 3 significant figures, 4.00 meters per second squared. So tangential velocity is just, this is one way to look at it here. It's just a change in that tangential, or what did I say? I think I said that wrong. Tangential acceleration can be thought of as just a change in tangential velocity. Okay. Now part D says find the magnitude of the total acceleration. Well, remember, total acceleration was that came from the Pythagorean theorem. So A is equal to square root of a sub c squared plus a sub t squared. And I feel like this is getting a bit squished, so I'm going to come down here and do it. That would be 6.25 squared plus 4.00 squared, which is going to be 7.42 meters per second squared. So as a last little conceptual question here, right at the end, they have a question. If the right at the bottom, there we go. If the force causing the centripetal acceleration suddenly vanished, would the car A slide away along a radius? Oh, I know. Okay. Proceed along a line tangent to the circular motion, or C, proceed at an angle intermediate between the tangent and the radius. Right, so if we have some So if some object is coming around here and suddenly the centripetal acceleration, which is pointing this way towards the center of the circle, would the object launch, let's see, it says part A is slide away along a radius. So part A is like, would it go like this? Part B says tangent to the circular motion, so would it go like this? That's B. And C says somewhere in between, some angle intermediate between the tangent and the radius, so I'll just say like, oh, maybe like this, C. So which one, A, B, or C? Oh, okay, so it would move in whatever direction its velocity was pointing, right? If the acceleration suddenly disappeared, then it would continue in whatever direction the velocity vector was telling it to go, which would be tangent to the circle, so it would be B. So if this was some object tethered to the center of this, well, I didn't exactly draw, this should have been tilted a bit more towards the center, but anyways, if it was like some object spinning around on a string or something like that, and the string was suddenly cut, then the object would continue to fly tangent to the circle. It would just fly off this in this direction. It would not fly off straight away like this. It would not be spinning around the circle and then line is cut and then just shoot off for some reason, just go off that way. That would not make sense, right? It's just gonna, if it's on a rope and then the rope is cut, it just keeps going whatever direction it was going when the rope was cut. Yeah. Yep. Okay, that is 7.3. So I will do 7.4 as a separate video.